issue of superposition, it seems to me that before you can talk about an external thing, you have to solve the superposition problem. And I didn't quite understand how it got resolved. But one thing, again, that Heinz used to emphasize was you've got two eyes, two ears. They're giving you conflicting signals. So if you have two measuring instruments, does that solve the superposition problem? And let you talk about an external object.
Well, let's see. Let me say several things. One, your distinction between constant and variable properties of objects is what we refer to as reference and pointer degrees of freedom in our work.
Okay.
I mean, that's physics language that comes from the pointer on an old voltmeter or something. That's the thing that moves that you're interested in, and everything else you're not interested in. It's just what lets you identify the instrument. And physicists tend to ignore the non-pointer variables, which I think in large part is responsible for the quantum measurement problem.
Okay.
As a philosophical and theoretical issue, because if you have to identify the system, it clearly can't be in a superposition of any of your identifying variables, right? If I identify my laptop by its position on my desk, then it can't be in a position superpositional, or I'll never identify it, right? So that's my criterion.
So the superposition has to be in the pointer variables?
You can only see superpositions in the pointer variables by definition.
Yeah, that's nice.
So in a sense, as you were pointing out for elementary particles, you do have to have two measurement instruments or reference frames or concepts or whatever you want to call them. They do have distinct semantic roles by definition. So they aren't just syntax. And one of them has to be a reference that you keep fixed in order to identify the system. And the other one you can allow to be variable to get some interesting information. I mean, the system having the properties that define it is not interesting information. The system being identifiable or not is interesting information.
Right. Okay.
If you look at things like electrons, identical particles of any kind, we distinguish them by spatial position, which, if you take a field theoretic perspective, is a completely artificial variable. No, they're in fact identical things, and the fact that we think that one of them's over here and one of them's over there, from a field theoretic perspective, these are just field excitations.
Okay.
So there's no such thing as a distinction. You just have two of them. So yeah, okay. I think this is all very much on the right track from a physics perspective. That one has to include these kinds of distinctions in a description of the physics itself, or you get things that don't make sense, like the measurement problem.
Is that still considered to be not understood?
Oh, yes. It's very much. I think everything I'm saying is very much a minority position. Yeah, most people don't talk about system identification in physics at all. And engineers talk about it every day.
Oh, really?
Physicists tend not to talk about it at all.
Huh. Oh, I see. You mean the engineers saying, okay, here's the one box, here's the other box, and they talk to each other.
And here's how I tell them apart. And here's how they tell each other apart.
Right. And the physicist is saying, well, okay, here's the needle, but never mind the housing and all the rest of that.
Right. Yeah. You'll see papers that say that explicitly.
Huh.
There's there are two very well-known papers by Max Tegmark at MIT that talk about decoherence. And in both of them, he uses exactly the same diagram, which splits the universe up into three pieces. The part of the observer's mind that observes the pointer state, and then everything else, which is the environment. So that builds the whole object identification process just into some feature of the external environment that we won't talk about.
Huh.
I love the distinction, things you can change and things you can't change, and also telling things apart, because in biology, I think what we see is it's like the ship of Theseus business, right? So in a body, what varies? Well, all the molecular details vary all the time. Molecules come and go. In fact, cells come and go. But so you have to have a system that stays the same. So what stays the same? The higher level system stays the same. On the lower level, nothing stays the same. Everything is different. Within a couple of years, you're all swapped out, as I understand. So we have this. So this leads to a couple of, I think, interesting things. One is that in a cognitive system, you have a similar scenario where if you're going to be a coherent mind, what comes and goes are different thoughts. You don't want to be different every time a new thought comes in. Well, that's it. Now I'm right. So you have to have right. You have to have some kind of stable structure that can persist despite the fact that new thoughts, new experiences, all of this is going to come. But something has to stay. There's some kind of higher level structure has to stay. So this question of what are we invariant to, and how do we tell the difference? So when I see you, I'm not a Laplacian demon who says, well, that's not Doug because all the atoms are wrong. So that's it. I'm fooled. No, I ignore the microstates and they say, no, that's definitely you. And then cognitively, the same thing. Even though you've had a million thoughts and maybe today's thoughts are different than yesterday's thoughts, I can still, we can still sort of recognize each other. So I think that's interesting. And then going back to the pointer thing, another thought I had of the physics instrument, I wonder if the reason why for physicists everything is sort of bottom up and low agency or zero agency and mechanical is because all their tools are. And right, the voltmeter and things like that are very low agency things. So of course they only measure the microstates of things. You need a completely different apparatus like a brain or an artificial neural network or something to detect these high level invariants, like a being, whether a body or a cognitive being, that does not change when the parts swap out, right? So physicists have there's no apparatus that you have that will detect these large scale virtual governors, right? You don't see that. All you ever see is microstates, because, and you can tell me if I'm wrong, because what you're using is apparatus that always looks down at that level. But for example, if you're a biologist, you can use a different apparatus that's very good at detecting these things, right? So the brain is really good at detecting agency in the environment. It skips over all the details to that extent, and right, and so you use a different. Anyway, that's where my mind went for this stuff.
So that's nice for two things. One is for the physics instruments, they're simple like that, so that you get an unambiguous result. If it measured 10 things, you'd never really know what you had measured because you got some function, your output is some function of 10 things. Conversely, I realized as you were speaking that we always say, gee, I had a thought. We never say, my mind changed. So these thoughts are something we project into something external, even if it's inside our head, it's external to me.
Well, that's an interesting question, right? Can you, so we have a feeling of, we all sort of have an innate feeling of free will normally, but we know you cannot control the next thought that you're going to have. Whatever pops up is what pops up. You have some sort of long-term control in the sense that you can undertake practices that will change the statistical distribution of future thoughts you are likely to have, whether by education or meditation or whatever. So, you sort of have some hope of long-term changing the ensemble of your thoughts, but you have no hope of controlling what your next thought is going to be. And actually, this goes back to the other thing about you saying that you had representations. So I also feel like I have representations, but for example, Nick Chater would tell you you don't have representations, right? So he wrote this interesting book called The Mind is Flat. And Mike Gazzaniga has a model of this too, that where basically there's a part of your brain that does things, and then there's another part that tells stories about why they happened. And right. And so he would argue that, and I'm not saying I go all the way with him, but the argument is that the deep underlying stuff is a post hoc sort of story, and that basically, and you've got experiments. So here's a simple experiment, and there's a video of this on YouTube. But this old experiments. If you got there's an electrode in the brain of somebody who I think was being treated for epilepsy or something, and it happens to be in a center that makes him laugh. So when the experimenter pushes the button, the guy starts laughing. So he's sitting there thinking about something serious. The experimenter pushes the button. He starts laughing. You ask him, "Hey, why are you laughing?" The answer is never, "Well, I don't know. I was thinking about serious things. Then my mouth starts suddenly laughing." That's never the answer. The answer is, "Oh, because I thought of something funny." That's always the answer you get. So this confabulation, right? So we're definitely good at telling stories post hoc about stuff that happened. Whether that's all there is, I don't know. But some of it is. I think some of it is some of that. Well, I think Dan would say there is no binding problem because there is no binding. I think he would say that it seems like there is. Now that brings up another question of seems to whom, right? So I don't know. That's still, I still find that a little tough. But he's been battling for years this idea that there is any executive control that binds it all together, and basically saying that it's a set of parallel processes which occasionally sync up with each other long enough to tell a coherent story, but mostly it's just independent modules that do stuff. So and that's what's super interesting. This idea of representation to whom is really interesting. So Josh Bongard and I just wrote this paper on polycomputing, and the idea is, is there an objective story, an objectively true story about what a given algorithm is computing? And so he's got this really cool data paper where you can show that he's got some sort of a porous medium that if you look at it one way, it's computing one logic function. If you look at it a different way, it's the exact same process is computing a different function. And so now you've got this idea that to even say what such a simple thing is computing is also observer dependent. And so you could imagine, right, that the brain and everything else in our bodies, there are multiple observers that are looking at these things in different ways and reaching different conclusions about what the heck is going on, right? It's we looked at, for example, gene regulatory network models, and you can do the same thing. You can say, without changing this thing at all, can I find a perspective from which the action of this thing looks like associative learning? And there are 6 different kinds of memories that you can find if you just look at it in the right perspective. And so then you reach, I think this is kind of an interesting philosophical question. Somebody writes an algorithm and you reinterpret it a different way. Is your opinion of what it's computing as valid as the guy who wrote it? Because that person will disagree. He'll say, "What are you talking about? I know what it does. I wrote the darn thing. This is what it does." But you're free to interpret it in a different way if you can make it work out for you. So, right. So that, I think that maps onto the neuroscience nicely. And why, and the other thing that bugs me, this has always bugged me, is if that's true, why is it so easy for our verbal module, whatever it is, to interpret our own brain states, and it's so damn hard for neuroscientists to interpret somebody else's brain states, right? Like neural decoding is really hard, but we do pretty well. Like not, not perfectly, of course, but I think we do pretty well with our own brain.